This video will be a review of Hilbert polynomials of graded modules of a graded ring and a brief introduction to the Hilbert polynomial of a projective variety. Discuss both the classical and modern approach with a focus on examples and explicit computations. So let M be a graded module of a graded ring S, and ring S is generated over a field K by various elements x0, x1 to the xn, and we define the Hilbert function of M, denoted by little h of M, from M to the dimension of the graded piece Mn. This is well defined as each graded piece Mn is a finite dimensional k-vector space, and we will be interested in the case when M is a coordinate ring of a projective variety. Let's first compute a simple zero-dimensional example. This example also illustrates that the Hilbert function depends very much on the embedding of the variety into projective space. So let x be three distinct points in projective plane. Then its homogeneous coordinate ring M is the following. And the vanishing ideal at x consists of all homogeneous linear polynomials vanishing at p1, p2, p3. So the grade 1 part of the vanishing ideal has dimension 1 if the 3 points are collinear, and its dimension 0 otherwise. And our Hilbert function at 1 is 2 if the 3 points are collinear, and is 3 otherwise. And what about hx2? To compute it, we have to understand what is the dimension of ix2. We pick representation v1, v2, v3 from a fine space A3 of the 3 points p1, p2, p3. And we define a map phi from k x0, x1, x2 to the vector space k3. Phi is given by evaluation at the point v1, v2, v3. And then kernel of phi is what we want at x2. Therefore, the hx of 2 equals the dimension of the image of phi. But indeed, phi is surjective. To show that, we have to show that the image of phi contains the basis vector 1, 0, 0, 0, 1, 0, and 0, 0, 1. To show image of phi contains 1, 0, 0, we let L2 be a homogeneous linear polynomial vanishes at P2 but not at P1, and let L3 be a homogeneous linear polynomial vanishes at P3 but not at P1. Then L2 multiply L3 vanish at P2, P3 but not at P1. Then phi of L2 multiply L3 is a multiple of the vector 1, 0, 0. So 1, 0, 0 is in the image of phi. More generally, if x are d distinct points, then the Hilbert function is constant d for m greater than d minus 1. Next example, we deal with the double point vx0 square in projective line, and we show that Hilbert function does not see the reduced structure. Let x equals vx0 square in the projective line. Then the coordinate ring gamma x is this, and the graded piece of the coordinate ring is gamma x m. And it is spanned by 1 when m is 0, and it is spanned by these monomials when m is greater than 0. So the Hilbert function is 1 when m is 0 and is 2 when m is greater than 0. It is the same as the Hilbert function of two distinct points, which means that we cannot distinguish between two distinct points and the double point vx0 square. In above cases, we have seen that the Hilbert function eventually stabilizes to a constant function. In general, the Hilbert function will stabilize to a polynomial. This leads to the definition of Hilbert polynomial, and it is due to the next theorem. Let M be finite generated graded module over S. Then there exists a polynomial PMZ of rational coefficient, and for M great enough, the Hilbert function will coincide with the polynomial Pm. In previous examples, the Hilbert polynomial and the Hilbert function do not coincide, but there are cases when they are exactly the same, as the following examples. We take x be the projective line, and the coordinate ring is gamma x, kxy. Then the graded M piece gamma xm is spanned by the monomials xm, xm minus 1y, and to the ym. So the Hilbert function at m is m plus 1 is exactly a polynomial of m. Next example is analogous to the general projective space. Let X be the projective space of degree D. Then its coordinate ring gamma X is this, and gamma xm is the span of monomials of total degree m in x0, x1, xd. So the Hilbert function is this, again a polynomial of m. Next, we consider the hypersurface in the projective space. Let X be a degree D hypersurface in Pn. Then there is an exact sequence of graded S module. And from S minus D to S is by multiplying F. Then take the M graded piece of this exact sequence. We will have a Hilbert function Hx at M is this. And we consider next example, which is the union and intersection of projective variety x, y in projective space. Consider the short exact sequence. And this map is given by f to ff, and this map is given by fg to f minus g. Then the first term we have therefore and this term we have and we conclude that hx intercept y is 0. So from the exact sequence we have Next, we use Hilbert polynomial to define the degree of a variety. A geometric way of defining the degree is to take the number of points of intersection of a general hyperplane with the curve. For example, a circle in CP2. It should have degree 2 since it intersects with the general line with 2 points. Roughly, general encode the condition that you do not want the hyperplane to contain the curve, and you also do not want it to be tangent to the curve. This definition is certainly accepted, though it can be difficult to work with, but the Hilbert function allows us to compute the degree of an algebraic variety. So let's give the following definition. Let X be an embedded projective variety of dimension R in the projective space. Then the degree of X is defined by the factorial of R times the leading coefficient of the Hilbert polynomial. Then we compute the degree of some varieties to show that it coincides with our intuition. Next, we compute the degree of hypersurface in projective space Pn. Let X equals V of f, where f belongs to k x0, x1, xn to the graded D part. Then we have already known its Hilbert polynomial is this. And since the dimension of X is n-1, so by our definition, the degree of X is the factorial of n-1 multiply its leading coefficient. So it is exactly D. A homogeneous polynomial of degree D cuts out a hypersurface of degree D, quite coincide with our intuition idea of degree. Next example, suppose X be finite collection of distinct points. Then the dimension of X is 0, and the Hilbert polynomial is constant. So the degree of X is again D. Next example illustrates that the degree of X depends on embedding in projective space, just as a Hilbert function. From previous example, we have known that the degree of P1 is 1. Let's compute the degree of its embedding in projective space PD, where the Veronese embedding. Namely, VD is defined by from the coordinate xy to all monomials of total degree D in X and Y. Then the induced map VD star on homogeneous coordinate ring identifies the graded pieces kxym with kxydm. So the Hilbert polynomial is dm plus 1. And its leading coefficient is the degree. Next, we show the geometric meaning of the degree of X by a specific example. Let S be the variety in the projective space defined as the 0 of yz minus x squared. This is a degree 2 hypersurface, so we would like to show that a general line in P2 intersects s at 2 points. To see this, we will work in the affine chart. Let L be any line in P2. Then, so long as b not equal to 0, the S intersect L belongs to the affine chart. And moreover, we can write explicitly where the little x is this, and little y equals, and these are usual coordinates on affine plane A2. Provided that a squared minus 4bc not equal to 0, then S intersect L consists of exactly 2 points. Furthermore, the collection of lines satisfy b not equal to 0 and a squared minus 4bc not 0 are both open in the Grassmannian, so their intersection is open as well. Therefore, a general line L in P2 intersect S in exactly 2 points. The geometric meaning of the degree of a projective variety is best described by Bézier's theorem. The theorem is as following. Let X be projective subscheme. The dimension of X is greater than 0. Let F be homogeneous such that no connected component of X is contained in VF. Then the degree of X intersect VF is the degree of X multiply the degree of F. The classical application of Bézier's theorem is to describe the number of points of intersection of two curves in the projective plane P2. The most well-known case is the following example. Let C1, C2 be two curves in P2 defined by homogeneous polynomial of degree D1 and D2. Assume in addition that C1, C2 do not share common irreducible component. Then Bézier's theorem says the degree of C1 intersect C2 is D1 multiplied D2. That is, C1, C2 intersect in D1 multiplied D2 points. Of course, we count these points with multiplicity. In next lecture, we will discuss the cohomology version of Hilbert polynomial, which means that given any coherent sheaf F on the projective space, the Hilbert polynomial of F given by the Euler characteristic